Physics chapter 19 theory video 12 energy changes in simple harmonic motion. So as you saw in the explanation, simple harmonic motion is there is a equilibrium point, it goes to one side, then returns to its original position, and then goes past that, then comes back to this position. So this keeps happening repeatedly. That is what we refer to as simple harmonic motion, and that is something that you have already discussed and you have understood. Then so how does the energy change take place in here? It is actually quite simple to understand. During simple harmonic motion, there is a constant interchange of energy between two forms, potential energy and kinetic energy. Now how does this happen? That is in a perfect world, that is if there is no change, if there is no loss of energy due to friction if energy is not lost as heat energy, this will continue to happen. This transfer of energy, that is from kinetic to potential and potential to kinetic, it will continue to happen, right? So that is the theoretical possibility. So now if you look at this mass spring system here, you will be able to see that when this object is pulled to one side, right? When the object is pulled to one side, as you can see, there is a potential energy now in this part in this part. So there is a storing of energy, right? So there is stretching that stores energy, then compressed part also stores energy. So this results in the back and forth movement of this object, right? When the mass is pulled to one side, one spring is compressed and the other is stretched. The springs store elastic potential energy. The ones that have been compressed also has elastic potential energy because it can spring back to its original position. Then things which have been stretched also has elastic energy stored because it can go back to shorten it by within elastic potential energy. So then when it is released from this point, it moves back to the equilibrium position and it accelerates as it goes. Then once it passes the, when it is accelerating, that means it gains kinetic energy. So that whatever the stored potential energy, elastic potential energy, is converted into kinetic energy. Then when it passes the equilibrium position, it reduces or it decreases in speed. That is, it is decelerating. So that means it is converting its kinetic energy back into potential energy, right? And this happens continuously, at the extreme end. When it comes to the extreme end, then that means its potential energy is lost, it is kinetic energy totally. So it comes to a momentary stop. Momentarily it will come to a stop and then returns back to its passing the equilibrium position to where it was originally. So like this happens back and forth. So considering the oscillations are undamped and also there is no energy transfer or decrease due to friction or any other force that acts against this, then the total energy in the system will remain constant, right? Then we can represent these details in graphs, right? These energy changes can be represented in two ways. Figure 19.22, that is this one here. This one here will show us that the kinetic energy and elastic potential energy, how they change, how they interchange with time. Potential energy is maximum when displacement is maximum, right? Whether it is positive or negative, potential energy is highest when the displacement is maximum. Kinetic energy is maximum when displacement is zero, right? Kinetic energy is maximum when displacement is zero. the total energy remains, that is displacement is zero, means kinetic energy is at its highest at the equilibrium position. The total energy remains constant throughout. That is, we are assuming that there is no energy waste. Note that both kinetic energy and potential energy go through two complete cycles during one period of oscillation. This is because kinetic energy is maximum when the mass is passing through the equilibrium position, moving to the left and again moving to the right. The potential energy is maximum at both ends of the oscillation. A second way to show this is to draw a graph of how potential energy and kinetic energy vary with displacement. So it is this 19.23. Right? So the total energy is shown by the green line. It remains constant at the top. Then potential energy is at its lowest at the equilibrium position. Kinetic energy, which is shown by the red line, is its highest at the at the equilibrium position, as you can see. Right? So those are the details that you need to understand. I hope you understood. Let's write down a note and then go to the questions. Then you will be able to understand this a little further. Write down energy changes in SHM. During simple harmonic motion, there is a constant interchange of energy between potential energy and kinetic energy. Then please pause the video and draw this figure 19.21. Then after you have drawn, please write this. When you have stretched the object towards one end, both the springs store elastic potential energy to get back to its original position, to get back to its original shape rather. When it is released, this stored potential energy converts to kinetic energy as the object accelerates towards the equilibrium position. At the equilibrium position, the object has its highest kinetic energy and as it passes the equilibrium position, it begins to decelerate and kinetic energy converts into potential energy back again. Assuming there is no loss of energies, all of the kinetic energy at equilibrium position would have converted to potential energy at the extreme end, left or right. As a result, the total energy in the system remains constant. Total energy in the system remains constant. Leave a line and write. When this energy change is represented graphically, we can obtain two different representations. The first graph shows how kinetic energy and elastic potential energy change with time. Total energy remains constant throughout. And during a single oscillation, kinetic energy and potential energy go through two complete cycles. Potential energy is maximum when displacement is maximum, within brackets positive or negative, and kinetic energy is maximum at equilibrium position. The second leave a line and write. The second representation is how potential energy and kinetic energy vary with displacement. At any given point, the sum of the potential energy and kinetic energy would be the same. As you can understand, that is the total energy, okay, would be the same. And please draw figure 19.23. And for the earlier graph, you have to draw figure 19.22 as well. So make sure that you draw both of these graphs and try to understand what they mean. And once you have gone through these things, if you understand, please do question number 20 to 22. If you don't understand, if you need further explanation, please let me know.